So for the discrete time white noise acceleration model, it turns out that we have one quantity which is called the target maneuvering index, lambda, that's sigma Vt square over sigma W, which defines in full the solution. First, let's see the physical meaning of this. This is the ratio of the root mean square value of the process noise, that's the acceleration's effect on the position over one period, which is really sigma Vt square over 2, but without the 2. So sigma Vt square is twice the RMS position uncertainty due to the process noise. The denominator sigma W is the observation uncertainty. This is the measurement noise RMS value sigma W. So what we have is the ratio of motion uncertainty to observation uncertainty, both root mean square values. And after algebra, which is described in detail in the textbook, the expression of the velocity gain coefficient beta in terms of lambda is obtained as 1 over 4 lambda square plus 4 lambda minus lambda square root lambda square plus 8 lambda. So what we have here is a simple algebraic expression for beta and a similarly simple algebraic expression for alpha. So these two gains really depend on nothing but this dimensionless quantity, the ratio of two position RMS uncertainties, motion versus observation. And this is very interesting because that's the real quantity that we have to select in a particular system when we design it. Once those gains have been obtained, further algebra, we had really 8 unknowns to solve with some equations that turn out to be not worse than quadratic, as you can see from the final solution. 3 elements of P, P11, 12, and 22. There's the steady state, updated state estimation covariance matrix. 3 elements M11, M12, M22 from the one-step prediction covariance matrix, again in steady state, and the alpha and beta, so these were the 8. Simple elimination reduces this final expression. There were 2 quadratic equations and they turn out to be solvable explicitly. So putting back those solutions, the P11 is alpha sigma W square. So the position gain turns out to be also, when chosen optimally, when all the assumptions of the model hold, going to yield, this is a number that is between 0 and 1, the position estimation improvement or noise reduction factor with respect to single observation. If you would not use a filter but would use observations as they are, what you have is variance sigma W square. If you do optimal filtering in steady state, you will get alpha times sigma W square as your position estimation variance. That's very interesting. So this same term as the gain also gives you the optimal reduction in the uncertainty for position. There are similar expressions for the P12, this is the covariance between the position and velocity error, and P22, this is the velocity error. And this gives a plot of the steady state filter gain coefficients for this piecewise constant white acceleration model in terms of lambda, the maneuvering index. At the maneuvering index of 1, you can see it here, it is roughly in the 0.5 or so range. Beta, alpha is around 0.8, The next plot gives you a better ability to read here. So you can see alpha is a little bit below 0.8 and at lambda equal 1, and beta is around 0.5. So as the maneuvering index increases, alpha increases. Maneuvering index means more motion uncertainty. Remember, there's a ratio of position uncertainty in the motion to position uncertainty in the observation. So this higher gain that's needed, more reliance on the latest measurement, therefore the quality of the estimate is degraded, it is larger, its variance P11 is larger because it cannot use the older measurements. They become irrelevant very fast due to the fact that there's a lot of motion uncertainty. Similarly, beta will be between 0 and 2. There are some simplified expressions for low maneuvering index up to 0.1. Typical real-life scenarios would have maneuvering indices 0.1 is fairly low. Sometimes it's as little as that. Exatmospheric motion of ballistic missiles obviously is noiseless, so it's a lot lower, but we don't use such filters because there are other better methods. High maneuvering index will be 2, rarely would it get much higher than that. So alpha has a simple expression, square root of 2 lambda, for lambda up to about 0.1, and beta is exactly lambda. Now, here is a summary of some of the comments made before. A high value, high intensity process noise relative to the measurement noise, that means large maneuvering index, yields a high position gain, and the filter will attach large weight to the latest measurement and consequently little weight to the past data, resulting in less noise reduction. Now, the fact that it attaches little weight to the past data is a consequence of its optimality. Remember, this is an optimal filter in steady state under the assumptions, the modeling assumptions that were listed earlier. Now, a small lambda yields a lower alpha and more noise reduction. Very important to point out, a small alpha will not yield more noise reduction unless it has been optimally determined based on lambda and all the modeling assumptions hold. By just looking at the previous expression that said P11 is alpha times sigma W square, there is a possible impression that taking a smaller alpha will give you more noise reduction. The answer is no, you'll get less than the optimum if you change the alpha away from the optimum. So those hold for the optimal values of alpha and beta only. Another comment is that the gains alpha and beta cannot be chosen independently. They are both determined by the maneuvering index lambda. Let's take an example. We had an example in the Kalman filter where the model we used, now we have a name for it, is really a discrete white noise acceleration model. We'll use the closed form expression for the steady state gain and covariances that we developed and compare with the results of the covariance equation iterations. We expect that if everything is okay, the direct solution for steady state will yield what the iteration yields eventually when it reaches steady state. And these will be shown in the plots coming up. For two cases of interest, we have to use the non-zero process noise. Remember, the gains go to 0 if there is no process noise or the process noise intensity is 0. We take the cases Q equal 1 and Q equal 9. The Q0 is of no interest in steady state because nothing happens. The maneuvering indices for these two values with sampling interval 1, sigma v being square root of Q and sigma w being 1 are lambda 1 and lambda 3 respectively. So they are relatively high maneuvering indices. We have a table here that for maneuvering index lambda 1, the position gain in steady state is 0.75, the velocity gain is 0.5, as we also read off from the tables before. The position variance updated is 0.75, that's the same thing, because sigma w square is 1 multiplied by alpha, you get back alpha. The one-step prediction in position is 3 for this medium lambda. The velocity variances updated P22 is 1, predicted is 2, and the innovation variance you can also evaluate from one of the equations is 4. And for the high maneuvering index, you can see the gain is higher, in position is 0.9. The steady state position variance is same, 0.9. But now there's an even bigger jump in the predicted position variance, one step to the next. That's because the process noise had a variance of 9. So this is 915, and velocity variance again is significantly larger. So if you compare these steady state values with those plotted earlier in the figures 5322 and 3, parts B and C for the Q1 and Q9, turns out to be obviously exactly the same thing. Now, for the discretized, this is the second path we have to take in coming up with the explicit solution. As indicated earlier, part of the development is common between the two models. When you have to bring in the Q, the process noise covariance matrix, we have slightly different forms. So we'll now take the second one as the discretized continuous white noise acceleration model, where the process noise covariance matrix is given in 62212 rather than 6324, which is the direct discrete time model. All the equations are the same, and the only difference is the lambda square, the maneuvering index, which is the slightly different expression. So it's denoted by lambda c, the continuous time situation maneuvering index, is a t cube, q tilde over sigma square. You take the square root, sigma w square, obviously same sigma w in the denominator, but the numerator is square root of q tilde t cube, because q tilde t cube is again a position quantity. Remember, q tilde had the length square over time cube. So multiply with t cube, length square, take square root is length. So obviously lambda c is again a dimensionless quantity, has the same interpretation as lambda, not subscripted from the direct discrete time model, because that's where it is the easiest to see its physical meaning, even though it is not too difficult to see it here too. And we have again explicit expressions for the alpha and beta gains, given this time in terms of not directly the maneuvering index, but another quantity related to the maneuvering index denoted as U. The algebra really doesn't matter. Once you have the explicit expressions, everything is clear. Minor comment is a typo in the text. Instead of a 3, there is a 2 there. So what we have now, based on this, very similar curves that provide us the values of alpha and beta, this time in terms of function of lambda c. As before, it's convenient to go in semilog and log-log scales. One has a wider range, one has an expanded scale in the region of interest. And the updated covariance expressions from the direct discrete time model will be the same as in the discretized continuous time model we are handling now. So the only differences are the definition of lambda c, continuous time maneuvering index, and how the alpha and beta depend on this differently defined lambda c versus how the alpha and beta depended on the direct discrete time version of lambda. Here is the plot, and again this is a corrected version to the one in the text. Unfortunately there was the typo ended up also in the figure. So here's the expression of alpha, that's in the semi-log version of the plot. Clearly it goes to 1. Now beta, interestingly, in the continuous time version doesn't go to 2 as in the discrete time version. It goes to 1.3, almost a little bit below that. So there's a slightly different final result. And this completes the presentation of the alpha beta filters for the two cases, direct discrete time and discretized continuous time white noise acceleration models. Now we have the alpha beta gamma filter for the discrete time Wiener process acceleration model, which considers a piecewise constant Wiener process for the acceleration. The state equation is the third order system shown in 6331 with zero mean white process noise defined as the acceleration increment over a sampling period. One could define the same thing with the jerk, but it's more convenient again to keep the physical intuition. The target maneuvering index is defined in the same manner as for the second order model. Lambda is sigma vt squared over sigma w, but now sigma v is acceleration increment as opposed to acceleration from the second order model. And the steady state gain of the resulting filter, which is called alpha beta gamma filter, the wk converges as k goes to infinity to a vector of three constants g1, g2, g3. Again, the first one is the dimension is alpha, the second one is the dimension is beta divided by t, and the third one is gamma divided by 2t squared. And the reason for this is that to have a position measurement used in an update of a velocity state component, you have to divide by t, so multiply by beta over t. When it has to update an acceleration, you have to take a constant, divide by t squared. And the 2 is just put here for convenience, so it turns out some of the equations are a little bit simpler. And these are the three gains, alpha, beta, and gamma, for the piecewise constant process noise acceleration model. The alpha goes at the limit at 1, the beta goes at the limit to 2, and the gamma goes to 4. So these are the gains of the position for the position velocity acceleration state with position only measurements. And by the way, there are results in the literature when you have not only position but position and velocity measurements. In this case, you have a more complicated filter, not 3 gains, but 6 gains, but we are not going to cover this. So here are the more detailed semi-log plots of the 3 gains as a function of the maneuvering index. And what's now interesting is to take a look at a system design example for sampling rate selection. What we have is, if we have the liberty of changing the sampling rate, it is important not only how to design the filter, what will be the design parameters. In the case of this filter is really just the selection of the process noise, pretty much specifies everything, but also the sampling rate should be selected. So what we assume is we have an object that moves in one dimension and undergoes an acceleration up to 1 meter per second square, and the position of this object is measured at intervals of cap t with an additive zero mean white noise with standard deviation sigma w 10 meters. So this is the RMS measurement error, that's a sensor accuracy. We'd like to determine the sampling rate or revisit rate, that's 1 over t, such that the steady state position RMS error be half a meter. So the square root of P11 should be half a meter. We will assume that the tracking of this moving object is based on a discrete time white noise acceleration model with process noise standard deviation 1 meter per second square. So as you can see, we have a process noise selected at the level of the acceleration of the object. Okay, the original requirement for the position error translates into a noise reduction factor, P11 over sigma w squared. This is the noise reduction factor. Can we achieve this? It's really 1 over 400. The RMS 1 over 20 really becomes 1 over 400 in the variances. What kind of sampling interval would be needed for this? We go back to the maneuvering index, and this is the maneuvering index, sigma v t square over sigma w, and this is the lambda, and we write an equation how to relate this to alpha in this form based on 653, 29 and 14, which provides us for this alpha a t. So what we have now is an expression of the sampling interval in terms of the available parameters for the observation, the sigma w, for the motion and for the desired alpha. Is there a t matching this? So as you can see, that's a fairly short interval, about 200 Hertz sampling rate. It's extremely high. And the reason for this is, and on purpose this example is shown, that a 1 over 400 mean square noise reduction factor is very hard to achieve. For a static problem, an object of a fixed location, it will require 400 measurement of that fixed position. This is a huge reduction. If the object doesn't move and you make 400 measurements, what you obtain now is a variance of its estimated location equal to 1 over 400 times the measurement noise variance. So, practically we can now state that you can improve the position accuracy over the sensor accuracy, but not by such a large factor. This illustrates the limitations faced when a certain performance has to be met. And the performance requirement here was really unrealistic. Now, if we relax the desired accuracy, so the RMS error in steady state is 5 meters, then we would need a filter gain of 1/4, and this yields a sampling interval of about half a second, and that's a more reasonable revisit rate of about 2 Hertz. So what this shows is you have a performance, you can calculate some system parameters, in this case the revisit rate, to achieve it. If it is unrealistic, in this case was very high, you have to go back and rework what is achievable with a reasonable system. And we have shown that the 5 meter accuracy, yes, it is achievable. This is an RMS reduction from the 10-meter measurement of standard deviation by a factor of 2, a mean square reduction by a factor of 4. Therefore, I would have to use a filter for which alpha is 1/4 is the optimal, so I have a t of about half a second, which is reasonable. You can carry out similar operations if the requirement is expressed in terms of a velocity accuracy. And really what this leads to is you can do a trade-off study between the sensor accuracy, sigma w, there's a measurement of standard deviation, and the revisit interval. Now, all this said, you have to keep in mind that the above relies on the discrete time white noise acceleration model, which, like any model, is only an approximation of the reality. Alternatively, we could use a discretized continuous time white noise acceleration model or a deterministic model, as has been shown in the very beginning in section 114. So what we have is, here is a model, here are some results for system design and parameter selection, but you have to keep in mind that none of the models are perfect. So you might have to go back and revisit the same problem with a different model. And the problem here is that if the process noise assumption for a piecewise constant discrete white noise acceleration model are valid for a given t, they cannot be valid for any other t unless it's an integer multiple. On the other hand, the discretized continuous white noise acceleration model is valid for any t. The underlying assumption that you do have a continuous time white noise acceleration is really an idealization. So, neither approach is perfect. This is why the designer has to have a good understanding of the underlying modeling assumptions. So, you need to know which model makes what assumptions, how close they are to the reality, and then possibly try several models, carry out the trade-off, and eventually have to do some simulations on an actual scenario. To summarize, we have taken a look at the alpha beta and alpha beta gamma filters, and we considered discrete time kinematic models with zero mean white process noise, which model either the acceleration that resulted in a second order model or acceleration increments. This resulted in a third order model per state, per coordinate in the physical space. The object might be moving, so in each coordinate will be third order or second order. This is the Wiener process acceleration model, and with noisy position measurements. For these, we have found explicit expressions of the steady state filter gain and the corresponding covariance. These filters, called alpha beta and alpha beta gamma, are the simplest possible because they use fixed, pre-computed, easy to pre-compute steady state gains. Consequently, they are clearly not optimal in the initial transient period or if the noises are non-stationary. The gains of these filters depend only on the target maneuvering index. The target maneuvering index is defined as the ratio between the standard deviation root mean square values of two position uncertainties. Number one is in motion, the position displacement over one sampling interval due to the process noise for convenience multiplied by 2, and the observation uncertainty, namely the position measurement noise, RMS value or standard deviation. In motion in a multidimensional space, which is the real world, these filters are used independently for each coordinate. However, under certain extreme circumstances, one has to be careful that this decoupling among coordinates could lead to some instability. The two classes of models discussed were discretized continuous time models based on continuous time zero mean white noise, where the acceleration was modeled as a continuous time white noise in the second order case, or the direct discrete time model based on piecewise constant zero mean white noise. That is a zero mean white sequence. So either define it in continuous time and discretize, or go and directly define it in discrete time. These noises model the uncertainties, which are either acceleration or acceleration increments in our case, and they exhibit different dependence on the sampling period of the effect of the noises on the motion. The covariance of the process noise over a certain interval for the discretized version or direct discrete time version behaves differently. None of these assumptions can model exactly motion uncertainties or target maneuvers, which are neither zero mean nor white. Actually, they are not random. But the state models, which have to be Markov processes, require the specification of some randomness, which, as we indicated earlier, is reduced to some kind of white noise at the input to the system. So we need a Markov process, we need white noise somewhere, we just have to decide where it enters, through what order system, second order, third order, and this, in spite of being definitely not an accurate model, is a reasonably good model because it works in practice. So, in spite of these mismatches to the real world, they have been used extensively in real-time implementations of target tracking, frequency estimation in speech recognition, or navigation systems. All the GPS or global positioning system receivers use such filters to smooth the indicated position, speed, and course. The term smooth values of the state really in the literature are also used interchangeably with estimated values. In some cases, the rigorous term of smoothing is estimate past values, but they use smooth even for the current values. So there is ambiguity in the literature. Now, such fixed gain filters have been proven to be useful in implementations where there were very modest computation memory requirements. That's using old computers, cheap computers. What you have is fixed gain filters can operate very easily with minimal computational requirements, and they give reasonable results. Not very good, not optimal, but reasonable. A convenient application of these explicit results is to obtain quick but possibly dirty evaluations, back-of-the-envelope evaluations of achievable tracking performance, namely the quality of estimation measured by the steady-state error variances. If you know your sensor accuracy and you know the possible accelerations in the motion of an object, you can quickly evaluate maneuvering index, use those expressions or the curves, and look at the achievable accuracy. They can be also used for other system parameter selection or design of system, namely the sampling interval. Now, these kinematic models today are not used as much by themselves, even though there are many legacy systems running on alpha-beta filters. They can be used as elements in a set of models describing different target behavioral modes in the context of multiple model estimation algorithms. That will be the topic of chapter 11 we'll cover in a number of lectures down the line. So what we have is a good understanding of the physics of motion the relationship from the physics to the achievable performance on one hand. The second is how to design for different motion modes the state models, how to select the parameters of the state models which immediately have an implication on the filter gains and the filter performance. But the main thing in chapter 11, we'll see that the single model does not describe well all the situations for the motion of an object, because sometimes they move smoothly, sometimes they move roughly, more predictable over certain intervals, less predictable other intervals. Therefore, multiple models are desirable, and we now understand when multiple models can give performance improvement. One more comment. While I indicated that these filters are about from the mid-1950s, it should be remembered that they predate the Kalman filter, which was published in 1960. The original alpha-beta filter were obtained using purely heuristic arguments, looked like they are a good idea. They were analyzed from the point of view of control systems. They were shown to be stable, it turns out, under exactly the same conditions that when they are derived based on Kalman filter steady state solutions, they give you exactly like the alpha between 0 and 1, beta between 0 and 2 are exactly the conditions for these filters to be stable. So the original deterministic derivation now has been supplanted by a stochastic Kalman filter based derivation, because this really indicates also how to select the parameters and how we can use them in more sophisticated adaptive estimation algorithms.